Hey, I'm Dave. Welcome to my shop. If you've just stumbled across this video, this is part 2 in a 3-part series reviewing my ESP32 single chip spectrum analyzer. It won't make much sense if you haven't seen part 1, so be sure to go and do that first if you haven't already. If you have seen part 1, then you know that we'll be heading to the Oval Office where the magic actually happens. I'll play the part of the man behind the curtain, conveniently crafting a complicated app as though I'm doing it from first principles. And hopefully along the way you'll learn a little bit about the ESP32, audio processing in particular, and embedded programming in general. We're about to explore the LED Matrix graphics class, which does the heavy lifting of actually drawing pretty colors on the LED panels. All we need to do is implement setPixel to light a single pixel on our panel given the X, Y, and color. Then, just like a privileged rich kid, we inherit everything else for free with no work on our part.
Alright, it's getting a little chilly in the Oval Office here, so we've added a jacket to the situation. We're also going to add a new header file. This one is going to be LED Matrix GFX.h. Okay, we have a class that is going to inherit from the Adafruit graphics class. If we take a look at this, you can see that it is an implementation of another class, which is print, but the bulk of it here is to do with pixel setting and getting. And so it draws lines, it draws circles, it draws bitmaps, it does pretty much all the basics, including text, that you need. So if we inherit from this, all we have to provide is, I believe, getPixel and setPixel. And we'll do that in this class, along with some other features that we'll add for our own convenience. And that will give us drawing primitives on an LED panel, which is exactly what we need to draw a spectrum analyzer. And so, at a bare minimum, to get this up and working, all we need to do is provide DrawPixel. So we're going to provide 2 implementations, one of it a 16-bit color and then one of a CRGB color for our own convenience. But this is the core one that we have to provide in order for the Adafruit graphics library to be able to provide all the functionality that we just saw. But what's it actually going to do? All it's going to do is going to figure out what pixel within the display needs to be set, and it's going to set the color value for that LED to the color we specified. And that'll make more sense once you see the PLED's allocation and the getPixel index function. CRGB is a color class. Let's see if we can do a peak definition here. There we go. So it's got red, green, and blue, and they're all stored as 8-bit integer or 8-bit type. So it's 3 8-bit components for a 24-bit color value. We also keep track of width and height, and that's it for member variables. We'll put in our constructor and destructor. So the constructor goes through, initializes the base class, passes in its width and height, allocates the memory for the LEDs, doesn't care if it fails because it's going to fault, and that's how I'm going to know that it failed to allocate. And then it adds the LEDs to the fast LED controller, which is kind of a black box. We don't need to know that much about it. So we're going to tell it that we're using WS2812B style LEDs, what pin we're using, and the color order that our LEDs expect the color data in, because not all of them are the same. We set a default initial brightness, and that's all we have to do to get the LEDs up and running. This class also has to do some of the, well, it's not heavy lifting, but some of the grunt work, I guess, of color conversion, because Fast LED operates in the CRGB 24-bit color space, and Adafruit Graphics operates in 16-bit color space. Hence, we get to do some conversion. So I provide a from 16-bit, which will take a 16-bit color, and bring you back the 24-bit. That's a little trickier than it sounds because the eye is not equally sensitive to all different colors, and so they've used 6 bits for green and only 5 bits for red and 5 bits for blue. So when you unpack it, not only do you have to account for the number of bits, but you have to account for the actual brightness of the colors, and we'll have tables that we will paste in a second for those. Here is the relative brightness tables, and you could probably have done this with a map float function instead of table driving it, but the code that I found as an example table drove it, and thus I do as well. So you can see we still need to get pixel index so that when we are trying to set an XY pixel on our panel, it knows which LED in the whole sequential string of 512 LEDs it actually is, or 768 LEDs in this case. And so we need to add get pixel and get pixel index. This will look a little odd, and it's not especially well documented here because it kind of worked, and so I left it. What happens here is you provide an X and Y, and it has to look up, first of all, which panel of the 3 panels it is, and you have to know that every second row on the panels runs backwards because they're wired in a serpentine fashion. That's why we check to see if it's an odd row, and if it is, we reverse the Y direction. Oh wait, I know what will happen. It is, whoops, the booster off the Dawn. Now it'll all make sense. We've also added a simple get pixel, which, given the X and Y, looks up the index and returns the color value that's in the array. So if we want to know the color of an existing LED, we can ask for it by X and Y. And finally, show matrix, which just calls the fast LED library to actually show, which in turn calls the hardware to send out the square wave signal to turn on and off individually each LED. And that's a lot of LEDs, and it happens many times every second, but hey, it's a computer, so it's fast. Set brightness, pretty self-evident, but all you need to know, and I should probably add a comment here, is level is 0 to 255. And thanks to the magic of the fast LED library that does a lot of the low-level hardware control and talking to the actual WS2812B LEDs, all we have to do is pass it this array of color data in the show, and the rest happens for us. And like I said, we can treat it like a black box. You can actually go look at the fast LED code if you're curious. I had to write it manually because on my first pass, the fast LED library did not support the ESP32. In the meantime, they have added support, so I ripped out my custom code, which used the RMT infrared remote controller rather than hardware timing, but theirs works just as well, and it's much more flexible, and I don't have to maintain it, so I use theirs now. Okay, that's it for LED control. 2 more files and we're done, believe it or not. Let's add the next one. It is going to be a header file again. One of the header files we made a reference to in the beginning, but did not implement. Sound analyzer, one of the 4 pillars that we talked about. Okay, first off, a couple simple definitions added to the file here. First being the number of samples that we take, which is 512, and the sampling frequency, which is 25,000, which will work up to 12,500 hertz for us, which is about where our top band is, which is why that number is chosen. If you revise your visuals and you want to go higher, I've tried it up to 44,100, which is the sample rate for CDs, and that seems to work as well. We have a couple of compiler definitions here, which are really just debugging aids. One is to print peaks to the serial port. That means when it's calculating what the peak is in each band, it prints out some text with just numbers telling me what those peaks are and what they were before and after some changes. So for debugging purposes, I can see how it is processing audio. Show sample timing tells me how long it takes to do the sampling, and show FFT timing tells me how long it takes to do the FFT, and those again are all printed out the serial port depending on how these are defined. The next thing our sound analyzer needs is a set of band cutoffs. So this is when you look at, if you're familiar with a graphic equalizer, the band cutoffs are very similar to what we'll use for a spectrum analyzer. So here we have 10 hertz, 20 hertz, 25, 31. These are actually an ISO standard. Only the 32 band uses a standard. 24 band and everything else is fairly hand-tuned to generally look good as opposed to go all the way up to 20,000 hertz. And from there we can get right into the meat of defining our sample buffer class. First, we'll take a look at the private variables. Arduino FFT is a reference to the FFT library, and it is unclear to me whether I could have a single instance or one per buffer, but because I don't know what state it keeps internally, I am keeping one per buffer for now until I can prove it's not required. Max samples, again, will be the 512. Sampling frequency will be the frequency, obviously, that we're sampling at. Band count is how many bands, 16. V peaks, this is the raw float data of the peaks for each band. Input pin is the pin on the chip that is receiving the input. Old VU is a cached value of how big the VU, which is the overall loudness, was last time around because we dampen change in it a bit. So we'll see its use later and it will make more sense then. And finally, there's a mutex. So when you want to touch this buffer, you need to own the mutex. And so if you are the interrupt and you come in and you try to touch this buffer and can't, you don't have time to wait. So you just skip it and mark it as a miss. But if you are the user code and you're coming in and you try to grab it and the mutex is busy, that probably means that the interrupt currently has it. And so you wait around until the interrupt is done. That's what the mutex is for. As the next step, let's add our public variables and our constructor. So the constructor is going to come in and set all the variables. I won't read them aloud to you because you can read as well as I can, I'm sure. It does initialize the mutex, and you'll see that Visual Studio does not like this, but it's because I'm using the GCC compiler, which does. This is actually a bit of a weird definition, the way they've implemented this in the Espressif SDK, so I won't bore you with it, but don't worry about the little error. It's not going to be an error when it really compiles. So the mutex gets initialized and the buffer gets reset, which you'll see the reset function in a moment. On the way out, all it does is free the memory that we allocated. Again, you'll notice that I am not checking for allocation failures, and that's intentional. I want it to fail and explode in the memory allocator if that ever happens, because this code's pretty deterministic. It's not like an operating system where, well, depending on what people do with it that day. So if I actually get anywhere near RAM limits on this thing, since I'm using about 2% of the RAM, it's a serious error, and I want to know about it right away. So we discussed the mutex briefly, and here are 3 functions for dealing with it. One is to try to get it and immediately lock it, which calls vport CPU acquire mutex timeout with try lock now, which basically means either lock it or don't, but let me know which you were able to do. Wait for lock says go and wait for the lock and wait around until it's ready, and release lock does the obvious. It releases any lock that you currently hold. Above in the constructor you saw it call reset. Let's see what reset actually does. csamples is a count of how many samples have been taken and stored in this buffer, so it always starts at 0. We go through and we zero out all the memory, and we zero out the peaks. The next function we need to add is for band cutoff table. If you recall, we had the option of 8, 16, 24 bands at compile time, and at runtime we need to map that to one of the cutoff tables. So depending on the number of bands, it will return the correct table. Now, without going into a huge amount of detail on the FFT, which I don't want to do, I will say that if you pass it 512 samples, it will come back into 256 frequency buckets. And you need to know what frequency corresponds to what bucket, and that's what this function does. And so that means when I come back after having sent in 512 samples, I get back 256 buckets. If I'm looking at bucket number 193, what frequency does it correspond to, so I know what band to put it into. And that's what this function is handy for. The FFT function that we're about to add can be a bit tough to explain, and I'm not a math teacher, so let me perhaps just ramble a bit on how I think it works conceptually, and at the risk of making myself the laughingstock of the computer programming community, maybe it'll make some sense to a few people. Worst case, tune me out for about 30 seconds if you need to. The FFT is a process we apply to the audio sample buffer to get back the band peak information. If you give the FFT a set of audio samples, it will return back to you a set of numbers that describe how loud the audio is in each small slice of the audio frequency spectrum. But rather than dividing the audio spectrum into 8, 16, or 32 bands, however, it divides it into half as many bands as you give it samples, and each band is of equal size. The number of frequency buckets that come back is exactly half the number of samples that you provide. So consider our case of 512 samples. That gets processed into 256 equal size little frequency buckets. We then use the bucket frequency function that we saw earlier to map each of those 256 little buckets to the bigger bands on our 16-band spectrum analyzer. We look for the loudest peak in each of the buckets that corresponds to a particular band, and we use it as the overall peak for that band. So, restate it all at once, you sample 512 audio samples into a buffer, and the FFT function returns you 256 audio peaks that you then group into 16 bands. Draw and repeat. Hopefully that made a little bit of sense, or it will make more sense when you see the code that does that. The FFT function itself is fairly straightforward and simple because all it really does is assume that the buffers are filled out so that you have 512 samples in your VReal buffer, and it calls the 4 functions sequentially on the FFT. Major peak being the last one helps search for the peaks within the bands, and that's all you have to do. The next function we're going to add is acquire sample. That is the function that is called under interrupt to request a sample from the actual pin and store it in the VReal buffer. Because of the way memory paging works, we're going to have to mark this with a special attribute to keep it in memory at all times, because we can't have it quote unquote paged out when the interrupt fires. So that's what that does. When it comes in, because we're called under interrupt, we're going to count the number of interrupts and we're going to try to lock that mutex immediately. If we can't lock the mutex, we're just going to mark this as a miss, upgrade our count of misses, and bail. If, however, as is normally the case, we are able to get the lock, we check to make sure we haven't exceeded the number of max samples yet, and we read from the pin, store it in there, zero out the imaginary quantity, which is already zeroed in the reset function, but safely, and update the number of samples taken for this and overall. Here we go, seemingly a little out of order here, and go to the return data, which is get band peaks. It's going to return a peak data object, which is not yet defined, but is going to be simply a set of doubles, which is the vpeak data. So what this function is going to return is basically a pack set of 8, 16, 32, however many bands you have, doubles representing the peaks. So I'm showing you this now because now we're going to process the code that actually returns or gets those values. You want to see what we were returning before we produced it. Okay, next is our code to actually run through all the buckets after the FFT is done. So after we've sent it the 512 samples, it returns us 256 buckets. This is the code to walk through all those buckets and put them into bands. The first thing we do is run through looking for the overall peak, and that's what this little section of code does. Next, we look for the average, and then finally we run through all of the buckets, figure out what frequency they map to, figure out what band that maps to. If it's greater than what we already have for that band, put it in there. Of note is the fact you'll see we're always starting at 2, not 0, which means we're ignoring buckets 0 and 1, because they are effectively VU meters because they map to the 0 frequency domain, which means they just apparently represent the overall impact or volume of the samples, not a particular band. So you can use them as VU meters. I don't. I actually measure VU directly, but you could. You'll see these print peaks. If they're defined, it will actually run through and for each of the bands print out a float number representing the peak, and that way I can kind of see what's going on as it's processing. This, I even put my name next to it because it's my ugly hack. These are just numbers which I multiply the 16 spectrum bands by in order to make them look about right with pink noise, because audio is nonlinear and really we're going for the best display, not most scientifically accurate, and I found that these are the scalars that are best applied to smooth out pink noise into a flat spectrum and look good for pop music. In order to make our scale logarithmic, we're going to scale the data up exponentially and then divide it linearly. So, assuming G-log scale is 2, it's actually configurable via knob. We're going to go to 2 to the power of whatever's currently in the band. Next, we run through all the band peaks to find the overall band peak, and that's what we need to divide by in order to fit everything into the display. We do that quick calculation here, and we're actually, if you notice, going to 1.1 to overshoot by a little bit so that there's some headroom left on the display. That leaves us with, 10% for some transient loud drum beats that come in rapidly before the audio can adjust its volume. Also, we never boost the gain past 2 to the 26, and this is totally arbitrary, of course, but it's just a number that looked good and didn't amplify noise. So, One thing of note here is that the all bands peak, the number we divide by in order to scale everything into the display, we dampen slightly by taking the last all bands peak and doing sort of a fake running floating average on it and keeping track of it that way, although we always let it go up as rapidly as it needs to. So we do the maximum of the dampen down or the current max, which gives us the ability for the scale to go up as quickly as it needs but then come back down softly. Next on our list of to-do, it's actually a new class. Let's stay out of here. Class Sound Analyzer. This really could, really fries with that. This could really also be called the Interrupt Master, because what it does is it represents everything that happens under interrupt. Starting the interrupts, when the timers fire, scanning the inputs under interrupt, and so on. So our first piece of the recipe is our set of variables and our constructor. So the sound analyzer has a hardware timer, and that's the one that's going to fire under interrupt, and it has the two sample buffers, a front buffer and a back buffer. It knows its sampling period and its input pin, and that's all the state it keeps. The volatile or IRQ buffer here, it keeps track of which one is the front buffer. Earlier in the setup, you saw us call start interrupts, and here is that function now. So it creates a timer scaled for the 240 megahertz clock, that's actually an 80 megahertz clock on the timer side of the ESP32 chip, and it enables the alarm with the right sampling period and starts the timer. One thing that's a little wacky, and it took me a little while to figure out, it was a horrible bug on my part, was that when you're sampling the audio under interrupt so many times per second, you can't just in your mainline code talk to the other analog pins. Apparently that does not work to be doing one analog read on a core while an interrupt happens that goes and does an analog read on a different pin. So you really need to do some, at a minimum, IRQ contention, and what I wound up doing was just moving my input pin reading into the interrupt so that I know that it happens without contention for the other pins. Initially, scan inputs was done along with the TFT, but if you actually see it in practice, the TFT updates maybe every 2 or 3 seconds, and you want your input to reflect knob inputs much more rapidly than that. So that is why we do the input much more frequently than we do the display of the user interface outputs. And the final function that we're going to add here is really the clockwork of the whole mechanism. It is run sampler passed, and it's the one that's going to return the peak data. In a loop, it perpetually waits to see which buffer fills up. And as soon as one of the buffers, buffer A or buffer B, fills up, because the interrupt has done so, it is then going to check the inputs, reset the other buffer, swap the buffers, and then fall through, proceed, do the FFT, process the peaks, get the band peaks, swap the, or release the buffer, and let everything continue. So this is really the main core loop in a sense. And last but not least, probably the most complicated piece of code. In terms of the fact that it's marked with an IRAM attribute to keep it always in page, it is volatile because the IRQ buffer is manipulated under interrupt, and we have to cast away the volatileness of that pointer in order to call through it. Because I didn't want to do this constantly is why we moved this out into a static function that calls back into the class. It might seem a little weird, but it's because you can't call through a volatile pointer directly without disabling warnings, and I don't really want to do that. So, I don't know if it's hackier than disabling warnings, but it's the way it works properly without warnings, so there you go.
Thanks for hanging in there through the end of part 2. From here, we turn to the final chapter in part 3, which focuses on the Spectrum Display class. It cares nothing about audio processing or interrupts, and is instead focused entirely on how to draw the fancy display. From the outside looking in, the function DrawSpectrumAnalyzer calls drawBand 16 times. Drawband calls drawLine, and drawLine calls setPixel, and setPixel puts color data in the buffer, so you'll finally see an end-to-end call with lighting up an LED. We'll also compile and link the project, flash it on the chip, and see it in action.